heights of a ring.
So, thank you for the introduction, and I'm really glad to have the opportunity to talk here today. As you mentioned, I'm going to be talking about the classification of cohomogeneity actions on symmetric spaces of non-compact type. In particular, about some recent work with Jose Carlos Diaz Ramos and Miguel Dominguez Vázquez, my advisors, where we searched for a proceeding for classifying these cohomogeneity actions. So, first of all, of course, we want to arrive to this theorem where we propose that a cohomogeneity action on a given symmetric space of compact type can always be built in one of 5 distinct ways, which for the moment mean nothing, of course, but in one of 2 ways that Juanma mentioned before, which we call first-spherical and solvable type, when they produce a foliation, a regular foliation, or by extending actions from lower rank symmetric spaces, or products of lower rank symmetric spaces, or by a process known as nilpotent construction. So, first of all, of course, I should remind what a cohomogeneity action is. A cohomogeneity action on a given Riemannian ambient space M is a proper isometric action whose regular orbits, that is, if you want the ones of maximum dimension, are hypersurfaces. We are interested in this problem because we are interested in studying homogeneous hypersurfaces, and of course this is the same because a homogeneous hypersurface is always the orbit of a subgroup of isometries. So, of course, since we are interested on the study of submanifolds and not on how the group acts itself, we will study these actions up to orbit equivalent. So we say that 2 actions are orbit equivalent if they have the same orbits up to isometry. So this was a classical problem, for example, in space forms. Here you have the cohomogeneity actions in R3, which were classified by Somigliana and Tullio Levich-Vita, which are the spheres as orbits of SO3, the cylinders as orbits of SO2 times R, or the planes as orbits of R2. So, in our case, they are going to give us a fixed ambient manifold M, and we want to produce basically a checklist of things to do in order to classify these cohomogeneity actions. Of course, we want the space to have many isometries to have, in order to have trivial examples, so we will be working with symmetric spaces, which in particular are homogeneous. Thus, we can express them as a quotient of the groups, and we will be looking at, for closed subgroups of this. In this case, it will be the connected component of the isometry. Okay. As I said, take M to be a symmetric space of non-compact type. That means that it's a quotient of a non-compact semisimple Lie group by the isotropy at some fixed base point, or if you want a maximal compact subgroup. And while we're having, since we're working with symmetric spaces of non-compact type, we have some of these nice algebraic properties that Juanma told about before. So we have the Cartan decomposition, K plus P, where case the G equals K plus P, where case the isotropy Lie algebra and P can be canonically identified with the tangent space to our symmetric space. We have the root space decomposition. It's the same thing as before. You take a maximal abelian subspace of P. All of the brackets with elements of this A are self-adjoint and commute, so we have that these operators diagonalize simultaneously, and so we get a decomposition of our semi-simple Lie algebra in terms of common eigenvalues for all these brackets with A. As before, sigma will be the set of roots. One can define a sense of positivity on this set of roots, and between those positive roots, one can choose the ones which are not sums of other roots, which are the positive roots, sigma plus, and simple roots simultaneously. And these root spaces have some nice properties. For example, this one regarding two brackets, which tells you that if you take a vector in G lambda and a vector in G mu, and you bracket them, the resulting vector will be in G lambda plus mu. So, same as before, if we consider N to be the sum of all positive root spaces, we get a diffeomorphism of G, sorry, not a diffeomorphism, direct sum decomposition of G into K plus A plus N, and this induces a diffeomorphism at the level of Lie groups. And if one quotients by K, it turns out that we can always see a symmetric space as this Lie group AN with a left invariant metric. Particular symmetric spaces of non-compact type are diffeomorphic to Euclidean spaces, with a funny metric, of course. And so the first way to construct these cohomogeneity one actions will be to look for codimension one groups here. Of course, this will give us a codimension one submanifold of the space, which in fact will foliate the space by left cosines. So of course this all produce foliation. So, what is the first way to construct cohomogeneity one actions? To look for subalgebras, CC subalgebras using the properties of these root spaces. So, for example, if we take out a line of the abelian part, taking the orthogonal complement, it turns out by the properties of root spaces, A is in G0, so bracketing with things in A stay in the same root space. So this is a subalgebra, and thus it produces a foliation, which is what we call a foliation of Horst-Baker type. This is because for some nice choices of lines in A, this produces a foliation, well, the foliation of our symmetric space by Horst spheres. Same thing if we take out a line of a simple root space by the properties of these brackets. Subalgebra A plus N minus a line is a subalgebra, in fact, so it produces a foliation. Which we call Horst-Baker type, solo type. And in fact, it was proven by Jorgenberg and Hiroshi Tamaru that these are the only two ways to construct foliations by hypersurfaces in symmetric spaces of non-compact type, up to, of course, converse. So the difficult thing in our case is that we are allowing to have singular orbits. So what do we do when we have singular orbits? Well, when we have singular orbits, we can't have too many. We can only have one in symmetric spaces of non-compact type. And the rest of things are hypersurfaces around it. Sorry, tubes around it. So for this, I will have to talk about parabolic subalgebras, and I will help myself with this drawing. Here you see a line in the middle that will represent G0, basically. And you see two pyramids of points. The upper pyramid represents the positive roots, and the lower pyramid represents the negative roots. So on the first level, I will draw the simple roots. Since every positive root is a sum of simple roots, I will say that a point in second, third, fourth level, and so on, is exactly the sum of the roots that lie under it. So for example, this is alpha 1 plus alpha 2, because we have here alpha 1 and alpha 2, or this is alpha 1 plus alpha 2 plus alpha 3. I'm saying this with the negative roots. So what are parabolic subalgebras? We want to extend these cohomogeneity one actions from lower rank symmetric spaces. For this, we want it to be embedded in some particularly nice way inside our bigger symmetric space. In particular, this will mean that we have to have like a nice enough root space decomposition of the lower rank symmetric space that can be extended to the ambient space. So we take a subset of simple roots, and we define a set of subalgebras. Here we have M5, which has this complicated maybe expression, but it's just taking the subalgebra, well, the semi-simple algebra if you want, might have an abelian parameter, but which would correspond to the roots in the span of this subset of simple roots. So this thing from here, we take a phi to be the part of A that we are not considering in this previous algebra, and then phi to be the remaining positive root spaces. The sum of these three things turns out to be a subalgebra, which is what we call the parabolic subalgebra associated with this set of simple roots. And of course, since we have that AN is inside of this parabolic subalgebras act transitively on our space. So why is this nice? Because if we consider the orbit of the connected group corresponding to M5, so what will be corresponding to the roots in this span of the smaller set of roots through the origin, this is a totally geodesic submanifold in our ambient space, which is not only totally geodesic, but it's of course a symmetric space of rank the number of roots that we took. And in fact, we can in some way identify the set of roots for this lower rank symmetric space with the roots that we have taken here by just restricting them to a suitable isometry algebra. So imagine we have a cohomogeneity one action on this lower rank symmetric space that will correspond in some sense to a subalgebra of this M5, and we stick this A phi M5, which is a subalgebra because of the properties of these brackets of root spaces. We consider the corresponding group. It turns out that by proceeding in this manner, we extend the action of something in this group, which is called a boundary component, to the whole ambient space in a manner that not only conserves cohomogeneity, but also orbit type. So this is an easy way. We have here in the smaller manifold an action with a singular orbit to produce an action with a singular orbit on the ambient space. This is what it is known. It was introduced by Bernhard Tamaru as the canonical extension of an action in a boundary component. And finally, there's this third method, which I won't get into it, which is called nilpotent construction. Basically, it's something really algebraic and mysterious, which involves producing cohomogeneity one actions from some choices of subspaces of dimension greater than 2 in this M5, satisfying certain algebraic conditions which basically assure that the action is going to have cohomogeneity 1. And basically this comes from generalizing how the actions on rank 1 are built with singular orbits, because of course in rank 1 you can't extend actions from lower rank symmetric spaces. One important thing to say here is that so far this nilpotent construction method, but for rank 1 and symmetric spaces of type G2, has always produced actions which could be obtained but by extending actions on lower rank symmetric spaces. So yeah, going back to the theorem, basically it says that if we have foliation, this was the result by Bernard Damaro, is a foliation of course spherical orthogonal type. And if it has a singular orbit, it's either constructed as an extension of diagonal action. Here by diagonal, I just mean that the Lie algebra acting on this thing is the first XX on two isomorphic or homothetic rank 1 spaces, the canonical extension of an action with a totally geodesic singular orbit, and this had already been classified, or an action obtained by nilpotent construction. So, how do we go about classifying this kind of thing? So, if the action has no singular orbit, it was already known by this result by Bernd and Damaro that it must be one of these two. But the problem is when it has a singular orbit. So basically, we consider this H, which is a subalgebra of our big Lie algebra G, to be in a maximal proper subalgebra of G. And there's this nice result of thinking, classifying maximal proper subalgebras of semisimple Lie algebras, which basically tells that maximal proper subalgebras can't be two diagonal. So if we consider the composition of the semisimple Lie algebra into simple ideals, a maximal proper subalgebra basically looks like this, that is all the simple ideals but one, and then one maximal proper subalgebra of this remaining ideal, or all simple ideals but two, and then a diagonal subalgebra on these two remaining ideals. By diagonal, I mean, of course, these two remaining ideas might be, have to be, isomorphic, and then we just take the pairs xx. In the first case, it turns out that there's no problem because this is a product action, and product actions can be seen as canonical extensions, but by just taking a suitable subset of roots corresponding to the factors. And in fact, they have the H and the maximal proper subgroup have the same orbits. This is by dimension reasons, because this is a reductive subalgebra, and reductive subalgebras of proper reductive subalgebras of semisimple Lie algebras, the connected groups can't act transitive. In fact, this action, canonical extension of this action of this diagonal group, well, a group in the diagonal, turns out to have the same cohomogeneity as the rank of each factor. So this is where we get our hyperbolic spaces. It can be complex, real, quaternionic, or whatever. In the second case, we have to differentiate two cases. Either this maximal proper subalgebra in the simple ideal is reductive, in which case one can proceed quite analogously to the first case. So reductive subgroups acting, proper reductive subgroups acting on irreducible symmetric spaces have to have a totally geodesic singular orbit, and these have been classified by Bernd and Damaro, and the orbit of our H is just the canonical extension of this thing. And when it is parabolic, Bernd and Damaro also proved that the action has to either come from an nilpotent construction or a canonical extension of a lower rank symmetric space. So what one does now is here change M by B phi and repeat the process. So we get that our action is a canonical extension of a canonical extension of a diagonal action, a canonical extension of a canonical extension of an action with a totally geodesic orbit, a canonical extension of an nilpotent construction or a canonical extension of a canonical extension. Okay, this in principle is messy, but we proved that a canonical extension of a canonical extension, so extending an action through to a middle symmetric space and then to the ambient space is just the same as extending it directly, and doing a canonical extension of an action obtained by this nilpotent construction can always be obtained by nilpotent construction directly on the ambient space. So one repeats this process, eventually runs out of rank. So here is where we get the 5 items in our classification. Maybe I'll stop here, but I just wanted to say that the first 4 items are something that can be checked mechanically. I mean, it's just determining the boundary components that can be a product of hyperbolic spaces and writing the corresponding diagonal action, sorry. The first 2 ones are already known, and in fact we know the modular space of foliations. The third one is just going through the list of Bernd and Tamaru for actions with totally geodesic singular orbits. And the only problem that we have is the nilpotent construction, which in principle is you have to check it for the different spaces ad hoc, and it might be a difficult problem regarding representations of Lie algebras, but it is expected that if the space is nice enough, so for example, as Juan mentioned before, split symmetric space, we expect it to have all the actions that can be obtained by nilpotent construction to be obtained by extending actions of on lower rank spaces. So this was all.
Thank you very much. Are there any questions?
So could you give, maybe this is not the expression, could you give an explicit example of the fourth one? Like what's the easiest?
Yeah, so in fact I had some more slides, but for lack of time. So for example, this is the first classification of high rank symmetric spaces, because before this paper we only knew classifications on symmetric spaces of rank 1 and 2. So basically what one does is check, for example, we have here SL NR mod SON. One can check for the irreducible boundary component just by looking at connected subsets of simple roots in the Dinkin diagram. So for example, if you have here, one can take roots out of the beginning or the end, and the resulting space is just a smaller SNR. So one goes to the list, goes to this, and is able to write, depending on the algebras. Of course, we always give a description in terms of the algebras. Goes to the list, has this group, and the canonical extension is just sticking the remaining root spaces that you get in this A phi and M phi.
So for example, in the SO2 case, what's the group that acts on the higher rank symmetric space?
That might be difficult. It's one can write it, but it's a mess. So, for example,
then we can discuss it later.
okay. one can write explicitly the Lie algebra in terms of the root spaces. But,
Can you decide which of these actions are polar or hyperpolar?
all of them.
They are all.
They are of cohomogeneity 1. So
Of course, yeah, sure. Yeah, sorry.
and